So hello, welcome to Module 40, Principles of Representation Learning. By the end of this module, you ought to be able to define what a representation is and distinguish it from a model and distinguish it from a classifier. You ought to be able to describe and justify qualitative properties, somewhat subjective properties of good representations, such as invariance, expressivity, and so on. You ought to be able to explain how different training objectives, like supervised and self or unsupervised learning, shape different learned representations. And you ought to be able to implement and analyze small experiments having to do with representations and critically evaluate plots and embeddings of representations, also touching on ethical issues as per usual. So let's think again of our overall big machine learning pipeline from a high level. We're going to always start with inputs. And increasingly, as we're moving towards neural networks and deeper neural networks, increasingly the inputs are not going to be just points in space like they've been in like Two Moons examples, but they're going to be rich, noisy, original data. So this could be an image, a text sequence. It can still be tabular features. Those are still important. We're going to put our feet into graphs and audio a little bit. So of all possible inputs, we have one X input. There's a representation function called phi. This can be an encoder, a feature map, or an embedding model. We'll talk more about embeddings specifically in the next module, but in all of these cases, what we end up getting is a representation, which is the output of this function phi, of the original data. This can be a feature vector. This can be an embedding, again, what we'll see in greater detail in the next module. This can be the principal components. This can be a kernel representation. We've seen phi before. This can be a variety of transformations. But finally, once we have this representation, Z, we can feed it into a simple predictor called G, and this will produce our predictions Y hat, as we've seen many times before. So G can be a linear classifier, it can be a machine learning, it can be a multi-layer perceptron, and so on. So the representation is just Z, the transformation of X into some representation that can be useful for us to do some kind of prediction with. Representation learning is a broad concept. It's very broad. We're going to just kind of carve off bits and pieces of it today in this module. But it's basically the process of training a model so that the model itself maps raw data into this new space of representations, which we call Z. And this will make important tasks like classification, prediction, retrieval, generation, anything we care to do, a lot easier. And some foundational papers down here. But yeah, representation learning is just using machine learning in order to discover what good representations are out of the space of all possible representations, big Z. So, I mean, this is probably going to be intuitive to you already, but I might as well go through it anyway. Just what representations versus models, like what is the difference? So in classical machine learning, like we've talked about previously, features can be manually hand-designed transforms of raw inputs. So we saw in a previous module a example of, given a text of many words, what is the average polarity of those words in terms of their positivity and negativity according to some positive to negative dictionary. And you get the statistic, and that statistic, that average would be a feature. And then on the other hand, a model would be something like logistic regression or support vector machines, given those features as inputs. And those models can also be given raw input X as inputs as well. In deep learning, the representation, which we call here phi sub theta, is learned. This can be like what we call a CNN trunk. We're going to see CNNs a bit later. CNN is a convolutional neural network, just to make that clear. And this representation often typically has many parameters, theta. After you have all of these parameters producing this representation, then you have a simple head, G sub W, which sits on top of the representation. So you have like a lot of parameters forming a model that gets a representation of something, and that representation is so good that you only have to pass it through like a single layer, which makes the eventual decision. And this single layer can be a linear layer, a very shallow neural network, and so on. So sometimes we factor a big model into a few things. So in the representation I just mentioned, or in the conception I just mentioned, we have a backbone or an encoder, which is the first part, which produces the representation. And then we have the head, which sits on top of everything else. And this does the task-specific readout, like it does the classification, the regression, the generation. This kind of factorization, breaking it up into two parts like this, allows us to reuse encoders across tasks, freeze encoders and train cheap heads, and then examine representation quality. I think we probably won't come back to this too much, but I think it's worth a moment just to sit and think about this a little bit. These are important facts, right? So you can have a representation of, say, words that you trained on, tens of billions or hundreds of billions of actual words in training data. But then you get representations that are such good representations of language across a variety of domains that you can just take this, the representation as sort of a building block, and you don't necessarily have to do very much more training, right? So you have this, we call it a foundation model. So this backbone or this encoder is like the foundation of a variety of other kinds of models. Maybe this foundation model was trained on a massive proportion of all the data that exists on the internet, but it was never used specifically in a classifier to detect which of our modules in this class has the most machine learning content in it, or something like that. We could just take this foundation model trained on a variety of other tasks, and only on the small amount of data we've actually produced in terms of the slides of this course, we can train a little classifier on top to just kind of indicate, like, say something about the distribution of the text in these different slide decks. That's the first thing that came to my head because I'm looking at the slides right now, but you can come up with a dozen and a half other possible tasks that have never been thought of before. The point is that these backbones or encoders are just so good, and they're such good representations of language and meaning and all the varieties of possible uses that it becomes very easy to just plug and play essentially these backbones, encoders, or foundations, and just slap a little bit of a linear layer on top, and then away with you with your tasks. So this reuse is a very important aspect of these modern deep neural networks and encoders and so on. So it's worth mentioning for a while. Hope I get that point across. But it makes building machine learning applications and AI applications just so much quicker. Let's talk a little bit about good versus bad representations. So again, because we're humans, consider again a two-dimensional feature space where each point in this one represents an image of a digit. And the color is going to represent its actual label. This is from the digits data set. So a bad representation would have all digits kind of scrambled together, like there's no way of differentiating them. There's just a big blob of numbers, of data points. The distances between points won't correlate with any kind of meaning or anything that's useful for doing classification eventually. And if you want to slap a classifier on top of such a bad representation, that classifier, the thing that you're actually going to do a lot of training on, is going to have to be very complicated. Maybe it's going to have to be very deep. You're going to have to put in a lot of expensive work into it, or maybe it just won't work at all. So bad representation will have all of these characteristics on the left, and down here we have their principal components analysis breakdown. Here's the first two principal components of some digits data. I mean, to be fair, it's not too bad, right? Like, all of the threes over here are kind of, separate from all of the nines in turquoise and all of the zeros down here in dark blue. So there's a good amount of separation. There's also a lot of overlap over here in the upper left-hand or the upper quadrant. This is sort of what we would call a bad representation. In class, I kind of went on a little bit of a rant about the benefits of principal components analysis versus t-SNE as a form of representation. But there's always trade-offs, and things are never perfect. There's no silver bullet in machine learning. In this conception, in some sense, because all we have is a big blob of numbers, you're still going to have to learn these very nonlinear cuts through the space in order to train a classifier. On the other hand, a good representation, each digit would form a very tight cluster. Every cluster will be well separated from each other, so the distances between points have carry meaning. So a small distance indicates that these two data points are very similar. A large distance indicates that they're very dissimilar. And then ideally a simple linear boundary or some simple boundary will be able to differentiate classes. So when we take this representation, slap a classifier on top of it, and feed train the whole thing possibly, or feed the whole thing into an inference engine, it'll be really straightforward for us. So here on the right is another form of representation called latent Dirichlet analysis, or LDA. We don't have really much time in this course to get into it, but I can throw a citation or two into the discussion board. An LDA is basically another way of taking data and re-representing it in a smaller number of dimensions, but it tends to be, as the title suggests, aware of the labels when it's producing these dimensionality reductions. So here, I mean, like, it's not an insane amount of improvement, but there's a lot of improvement here anyway. You can see how some of these clusters are separated quite a lot more. So this purple cluster, which seems to indicate number 4, you can separate it in these 2 dimensions by basically, well, you can separate it pretty well by drawing a straight line between it and all other clusters, as opposed to here, where it's a lot more overlap between the purple cluster and the others. Similarly, the blue cluster 0 is highly separated from the others. You can draw another linear classifier separating it from the others. And quite frankly, a few linear cuts through the space is going to do a pretty good job of classifying these digits. Again, with some exceptions, there's no silver bullet. These 1s over here in orange and these, it looks like 7s in kind of gray, seem to have a lot of overlap, as you might expect based on the shape of these images. So there's a bit of an improvement as we go from principal components analysis to latent Dirichlet analysis, and according to the qualities we mentioned a moment ago. We're going to make this intuition precise in a moment through some actual experiments. Let's again scaffold our concepts. We have a representation function we call phi, which goes from an input space x to a d-dimensional vector of real values, where d is the embedding dimension. And speaking of dimensions, I'm going to zoom out along this one. There we go. That's what a representation is. We basically mentioned this already. A task-aligned representation is a function phi, where a very simple model on top of the representation it produces will perform well, that should be in quotes, I guess, on some task. Like, what is the definition of well? But yeah, if you have a representation that makes subsequent processing easy or highly performant, that's a task-aligned representation. And we like task-aligned representations because so much of what we do in machine learning has to do with performing well on tasks. A representation is invariant to a transformation, t. So you apply a small transformation to the raw inputs x, so t applied to x, and apply that transformation into our representation function phi. The result should be similar to the situation in which we did not put that transformation on x. So the phi of t of x is roughly similar to just phi of x, as if there's no transformation. So, add a little bit of noise, apply a little transformation, like a translation, like a movement up or down, or a rotation. Those are all possible transformations t. And if we apply those transformations, the representation, whatever it is, this vector of numbers, which has some kind of meaning to the model, should not change too much. That's invariance. It does not change. Equivariance is the idea that transformations in the input space induce transformations in the feature space, but they're very predictable. So in this case, again, we have a transformation applied to x. These can be a variety of possible transformations. So you change the input data, you pass that through our representation functions, which produces these representations z. Maybe now there's a change in our new representations, but those representations are predictable. So this is just one example of many, but it could be a linear transformation. So we have a phi applied to the original data x. That produces one representation. You have a transformation on x that would pass through phi to produce another representation, and the difference between these two representations would be a simple linear transformation of the original space, or indeed of the other one, right? So whatever the representations are, they just move linearly with the transformation that we apply to x. So here's an example, which again may be more salient when we talk about convolutional neural networks, but shifting an image. Like if you move an image around and you're doing computer vision on that image, then the representation of that image will change in a predictable way based on transformations to the raw inputs. Okay, we've already talked about invariance and equivariance in a previous module, so the same principles apply here. Invariance doesn't change, equivariance changes in the same-ish way. So there's no universal rule to what makes a good representation. We have the idea of them being expressive enough. So if they can represent the variability that you need to solve the task, so if a representation is too narrow and it can't really represent all the changes that can occur in the data or in the phenomena, that won't be very expressive. That's not a good representation. Are they task aligned according to the definition we just had? Ideally, does it produce representations that are linearly separable for the classification task? Well, that's a good representation according to what we just mentioned a moment ago. Are they invariant to nuisance factors? Nuisance factors are similar to the idea of noise, but they can come in other forms. So again, thinking of images of anything you want really, like if you change the lighting in the room, you backlight or light from the front, or you again rotate the image. If you're doing audio and the person you're trying to identify or the speech you're trying to recognize words in changes in pitch or slowness, does the representations suddenly become very different? And again, just regular noise. So if there's a lot of noise applied to an audio signal that you're going to pass into a speech recognizer, does the representation of that speech suddenly change a lot if there's a lot of background noise? Ideally not, right? Because you're mostly caring about the words that are being produced. Yeah, they're robust or invariant to nuisance factors. Are they stable and smooth? So again, this is more the equivariant thing, but small changes in input produce a small meaningful change in representations. This is related to something called Lipschitz behavior, which is beyond the scope of this class, but if you're interested, you can read more about it in this paper. Often we want them to be compact or efficient. We're going to see an example later today, which I'm very happy about the result, but sometimes you have a very, very high dimensional input data, and that can be hard to represent. You need many, many parameters through a deep representation to get good performance. So we'd like to kind of compress the useful information down as much as possible. So something like lower dimensionality, sparse representations, this can help with generalization and interpretability. So principal components analysis, for example, produces representations that are a lot smaller usually than in dimensionality than the original data. So that's an example of a good compact and efficient representation. And are they composable? So all of the features that we've produced in the vector Z, can they be reused across different kinds of tasks according to the generalization idea that I mentioned a few slides ago? Can they be combined in different ways also? This is maybe getting a bit ahead of ourselves, but it's kind of hard to pinpoint, this is the exact number in the vector that represents syntax in language, and this is the exact element or number in the vector that represents the meaning or some particular component of the meaning of a sentence. It's not quite so simple, but if you have the useful information in a task distributed across these vectors Z, can you combine them together in a way that is useful, that produces new meaning? Because that's going to be important if we're going to combine the data or the representations that are in Z in order to do some classification in the head we slap on the top of this big model. So this is kind of a checklist. So is it expressive? Is it task aligned? Is it invariant to nuisance factors and so on? This can be seen as kind of a checklist when looking at code examples. I hesitate to use the word checklist just because there's no single universal definition. Each of these things, each of these components are very subjective. So whether or not you check off an item in this checklist is going to also be very subjective. So leave it there, but just something to think about. I see I haven't scrolled this thing, so I'll try to fix this slide before I post it. But here's another example of a pretty but useless representation. So we have a two-dimensional t-SNE plot of patient health records. Not to pick too much on t-SNE again, but I will for now. We have a t-SNE representation of patient health records, and it produces this nice colorful graph, and all of the little clusters with the different colors are nicely distributed. And we use the word t-SNE, which is going to impress people in machine learning. We have a legend. These legend, we say orange represents this disease, red represents that disease, and so on and so on. But it turns out that there is a strong influence of the hospital ID where the patient was treated on the colors. So like a emergency hospital would have a lot more traumas than a like oncology hospital, for example, in which cancer would be more frequent. So the color for various kind, or the few colors for cancer in the legend might technically indicate the respective diseases, but those diseases really come mostly from this particular hospital. So information about the hospital has made its way into the representation without us actually knowing it on the surface. Hope that makes sense, because it's a very common problem in machine learning and representation in particular. So the problems here, among others, is the representation ended up encoding site-specific artifacts. So maybe there's scanner differences, maybe there's different practices, different approaches in the trauma hospital, versus the ER hospital versus the oncology hospital. Instead of like the specific biological signals or demographic signals that might matter in the patient data. So these clusters we observe in the TISNI, which again, like for good and bad, like they produce very differentiable clusters. These clusters will be driven by these nuisance factors that I just mentioned. They can correlate with other things also, like socioeconomic status, race, or insurance status. You have a hospital in an area that is less well off than another, will encode this sort of differential. We've seen lots of examples of this hospital A and hospital B previously. Actually, I think it's my other course, so strike that. But if you want to go to my class on 1109, we go into a lot of examples of hospital A and hospital B, and how they encode signals that we don't necessarily want them to encode. So a model trained on these representations, will perform well in validation data. So we acquired a lot of data from the oncology hospital and the trauma hospital. We separated them out. We trained a model on one. We're validating on the other, and things look good. But that's because we're using data from the same hospitals to validate as to train. Now suddenly you ship your model into a whole other city in which they have yet another collection of scanners, slightly different distributions of socioeconomic status, insurance status. Again, this example is more tuned to a country not Canadian, that in which insurance denies care for a lot of people, but you get the idea. And then it will just perform very badly. In fact, even in Canadian hospitals, when I lived in Toronto, sometimes a model trained in one hospital on data from that hospital would not generalize to another hospital literally up the street. Because of slight differences in lighting conditions, sensor conditions, and so on, unless you put the effort in retraining it and acted carefully and with truth-aligned approaches. So anyway, this would be a bad example for disease risk. It would violate all the kind of problems that we're talking about, and it would bake in these kinds of errors. So let's go into the math a little bit. If you have a K-class classification problem, so we're not doing binary classification anymore, we're doing K-class classification. Suppose the representation function will map the input X into Z, like we talked about before. We have a linear classifier in this representation space, so a given Z will classify what Z is. We would like to have something which is related to linear function only, right? So for each of our K classes, big K classes, we choose the little k that optimizes this function, and that little k will be our prediction y hat. So we're doing classification. And so the class K will have its own weight matrix and bias vector. And running each of these parameters, each of these K parameters through these linear functions, given a representation Z, which we produced with phi. We'd like the situation because this linear classifier is relatively easy to train and comprehend and so on. So if this classifier, if a classifier where we just choose the k that maximizes this function, then we say this is approximately linearly separable for this task, and we'd be happy because linear separation is sort of the easiest kind of baseline way of doing classification. If this function doesn't make too much sense, don't mind too much. You can go back to think about support vector machines and think about the straight lines cut through a representation space, representing binary classification, and just scale it up to k dimensions, and you get the idea. Okay, so linear classification of k classes is approximately linearly separable. it suggests that the representations Z are approximately linearly separable. Why do we like this? So these linear models tend to be convex for many losses, so the optimization is predictable, and usually, if you're lucky, there's not going to be any local minna or local optima, and that lets you get stuck, so you're going to end up with the best possible solution you can under these constraints. It'll be data efficient, so training a model won't require too many extra data points, which again, if you have a massive model producing the representation and you only have a small amount of data to do the training of a little layer slapped on top of the representation, because you have so little data, you don't want to do too much training. You want the required number of parameters to be small. So yeah, linear separability or linear models are relatively data efficient relative to massive deep neural networks. And indeed, the idea here is if you have a representation Z in which you have this linear separability, that suggests, kind of in a hand-wavy way, that phi has done the heavy lifting of untangling the classes and putting the different big K classes in different spaces in Z. So it kind of did a lot of the work in pseudo classification for you beforehand, which keeps on coming true in a lot of empirical experiments, one of which we'll just touch on later. We'll have two experiments, but only one of which we'll really touch on later today. So if X are the inputs and Y are the labels, Z are the representations, again hammering that idea home, we have two desirable properties, but these properties can sometimes be in a little bit of tension. Again, there's no silver bullet, and often improving one aspect ends up worsening the other. So we want task information to be preserved. We want to have a large mutual information between Z, the representation, and the output Y. So that representations will be predictive of the labels we want to predict. We're not going to go and reintroduce what mutual information is, but if you want, we can spend some time in class going over what entropy is, what conditional entropy is, and how those ideas come together to basically describe a measure of the shared information in the Shannon sense, in the information theory sense between these two variables. And we want the information in the label space and the information in the representations to be very close to each other, to overlap a lot, so that if you know the representations, you know the labels. Right? So that's the task information is preserved or represented well in Z. The nuisance compression means kind of like not including information of noise or nuisance factors. So U, imagine, is a vector or as a representation of the nuisance, like lighting, sight, identity of the nurses or doctors at the hospital, or the patients if we care about anonymity. So we want representations to not have what is in U. We want the mutual information between the representation Z and the nuisance U to be as small as possible. And sometimes these two things can be optimized at once. You can make the representation Z very representative of the task, and you can make the representation have almost none of this nuisance stuff you don't want. You can filter it out. But unfortunately, often this isn't the case. Often if you want a really knowledgeable, generalizable representation Z, which can be helpful for the task, sometimes it'll start also learning something about the nuisance. Maybe for some reason, again, to have an encoder, a foundation model that is very generalizable, it would represent almost anything you want it to. Maybe you want to have a lighting detector, maybe you want to have a sight detector for some reason for some task. So information about the sight ought to be encoded within representation Z, which would mean that the information between Z and U would be high, which kind of goes against the idea that we want to compress out or filter out the nuisance. So we very rarely compute these mutual informations exactly. I mean, this is just like high level and intuitive and theoretical. Sometimes mutual information is part of the training process, so I don't mean to discount that either. But the idea of this information bottleneck picture will be useful just conceptually for what we're trying to achieve in practice. So now consider we have a big encoder. So we have a neural network model that basically takes input and produces a representation Z. We'll call that encoder phi sub theta. So there's a particular parameterization of the neural network, theta, which produces this really good representation. And we'll have a simple linear head called G sub W. W will be the weights or the parameters for the linear head. If you have different training objectives, then this will push the representation phi sub theta into different directions. I'm going to go over this relatively quickly. This could even be a microscope sort of, a side-ish looking thing, but high level, I think there's not too much new going on here, so try to just focus on the high level aspects of what I'm about to say. We already have the supervised classification objective. We know what that is. That's the loss between the true label and what we predict. And what we predict is just the linear transformation of the parametric encoder of the input. So we take X, pass it through our encoder, gives us a representation, pass our representation through our linear head. That will produce a prediction, compare that prediction to Y. That's our loss. We know what the supervised classification objective is. This will encourage representations where the examples of the same class will cluster together and will be pretty separable from the other classes like we were talking about a moment ago. So that's what we've already talked about, but there are other forms of objectives for training that could produce different kinds of representations. The autoencoder is one of the preeminent ones, one of these. So here, what we want is a reconstruction of an encoding that is as close to the original inputs as possible. We talked a little bit about this when we introduced the idea of principal components analysis. So in that case, we had all this data. We compressed it down into a small number of dimensions, but given those dimensions, we wanted to be able to recreate the original input space as closely as possible. This is similar to lossy encoding I framed it in class. So you have an encoder which produces Z, which is the representation, but then you can pass this representation Z into a decoder. So you've encoded the information, now you want to decode it. The decoder has its own parameters, psi here. The idea is it produces a representation in the original space, call it X tilde. So I think we've all seen like decoders in other forms, same idea here. So an objective for an autoencoder, something that is trained just like it doesn't care about labels, is basically doing something like unsupervised learning and trying to learn really good representations of the input and the input only. So what you want is to have something that encodes into a small representation space that can be effectively decoded back into the same space. And we want this difference between the original data and the reconstructed data to be as small as possible. So the squared difference, or the 2 norm of this difference, we want it to be on average as small as possible. And we want to produce the parameters for our encoder, theta, and our decoder, psi, to minimize this distance. This will encourage information preserving representations. So the encoder will be really good representations of X in a very compact way. It just might not happen to align with what our task is. And again, very quickly, just a third objective. This is from Chen. This is contrastive. We'll also see contrastive learning very briefly in the next module. The idea here is that we want to the representation for a particular data point X. So again, we have these encoders that produce representation Z. We will have some examples of positive classes, X plus, some examples of negative classes, X minus, in the case of like binary classification. And we want to have representations for X that kind of push positive instances close to each other and negative instances close to each other. If X is positive but it's close to a negative data point, we want to kind of separate those two things. This is very similar to the principle we were mentioning a moment ago, where classes are supposed to separate from each other as much as possible. This just makes it a little bit explicit. Whenever you have positive and negative examples that are close to X, you want to move X's representation in the direction of its appropriate class. So here the idea is you have representations where augmentations of the same input map close together and different inputs map far apart. We're going to see a little bit of this when we talk about self-supervised methods later in this course. So now some examples. So this first example is a bit of a mixed bag, but let's get back into it. We're going to compare a classical compression algorithm representation, PCA, that's going to map raw pixels for digit classification, and we're going to use our familiar load digits or digits data set for this task from sklearn. This is about 1,800 grayscale 8x8 images of digits. So you have 10 classes, 0 through 9. So every image is basically, will be 8x8 pixels, but you could unroll them into one big 64-dimensional pixel vector. And that becomes your input data point X. So we're going to train a logistic regression on the standard raw inputs. We're going to train logistic regression on the PCA compressed features, and then we're going to compare test accuracy and visualize 2D embeddings. We've basically already done this in a previous module, but because it makes sense here, we'll see it again. Here is the same old techniques. We're using sklearn's pipeline, and we're using sklearn's fit, so nothing too much going on here. We're using, this is the raw performance. Here we have I think the only thing I'll mention is we have accuracy score here is going to show us, classification report. Classification report is a function from sklearn metrics, which produces a table and some more information than we've seen in all of our previous examples. That's basically what we see down here. So for each of our classes, considering that class to be the positive class and all others to be negative, we have the precision and recall and F1 score for each class, and the number of data points that are part of that class. So we have about 52 to 55 data points for every class, and precision and recall are just fantastic across the board in most cases. Then we have a PCA representation. So again, we just take our data in a pipeline, we scale it, we pass it through PCA. We're going to have 32 components. Again, we pass this through logistic regression. We fit, and then we describe things using our results here. This is, again, we saw something very similar in a previous module. With raw pixel, 64 dimensions, we get up to 98.1% accuracy. With half as many dimensions, we get to about 95% and 95.2% accuracy. So I wanted to keep this in. So a couple of reasons, one of which is just to reinforce the idea that there's no silver bullet in machine learning that will just always work all the time. I don't want people to get discouraged because, well, I used representation, and representation was like a little bit more than halfway through the class, so I expected it to work well. Just because you're using representation learning doesn't mean necessarily that all your accuracies are going to improve. This is already a task for which the baseline is really strong. And I wanted to just give this negative result as kind of a reinforcement of the idea that things don't always go right, and to kind of just let you know that if you encounter similar situations in the future, that's not the end of the world. I do, however, want to also just also on the other side mention this sort of trade-off. It's true that the performance drops by about 3% here, but it does so by also having the dimensionality. So is a drop in 3% worth a model that is, speaking loosely, takes only half as much input? Maybe, right? For the purposes of scalability, maybe. Here's our two-dimensional representation, given the principal components analysis. We've seen this already several times, but ask yourself once again, do these classes form roughly separable clusters? What does separable mean? You can return to this very module to answer that question. Are some digits overlapping? Like some digits we expect to look similar, like 7 and 1, like 0 and 6. Do we observe that in our representations here in 2 dimensions? Answering those questions, does that tell you whether a PCA is a good representation for this task? Is it a bad representation for this task? You should be able to answer that question by now. So again, using our checklist from several slides ago, you don't have to necessarily remember all of these things, but it'll be a good idea to keep these different desiderata in mind for what constitutes a good representation. Are these representations PCA expressive? Just having just the 32 most highly invariant dimensions according to PCA expressive? Does it cover the overall manifold well? Is it task aligned? This is a bit maybe of a subjective call to make, but if the accuracy with PCA using 32 dimensions, if it's close to, or if it's better than, and potentially the baseline, has PCA retained most of the label relevant or classification appropriate information. Has it smoothed any noise? We haven't really observed that in this quick example, but questions to ask and answer with regards to task alignment. Is it invariant and robust? This is something you can do on your own, but if you want to add noise to the data, maybe if you can rotate those tiny little images a little bit, maybe flip them or maybe not flip them, but do some other transformations to the inputs. Does the raw models performance change a lot compared to any changes in the PCA representation models? Again, something to explore. Is it compact? Clearly, we have the dimensionality. This produces cheaper models. Maybe it could produce less overfitting for deployment. So these are just a handful of the checklist items from before, but ask yourself these things. Again, remember that PCA is unsupervised. The dimensions of PCA are based on whatever directions of the original data vary the most. So PCA doesn't care about the labels. We hinted that there are other models that produce representations that are sensitive to labels, like the latent Dirichlet analysis. Maybe there's some others. So keep that in mind for the example we just saw. And also keep in mind that this is a very simple task in which the baseline is going to perform very well. But let's try something a bit more complicated. Let's look at another image task, CFR10, in which the representations are going to have to be a lot more complicated or nonlinear. So here's our second example. So here we're going to compare a cheap classifier on raw RGB pixel vectors. So again, just flattening the images, like taking a two-dimensional image and flattening it out into one-dimensional vectors. And then we're going to train a classifier on those representations. We're going to train another classifier on more compact representations that come out of the second to last layer of a small convolutional neural network that's been trained to understand images. So again, we haven't really talked about CNNs before, but for now, just consider this neural network as just a encoder of phi, sub theta, where the theta is the parameters of this neural network. This data set is CFR10, which you can learn about at this link. This is somewhat bigger images. There's 32 by 32 color images. We're going to deal with 10 classes again. We're going to subsample about 5,000 training images just for the sake of speed. And then, again, we're going to train a small CNN. This is a bit ahead of ourselves, so just take it as read for now. We're going to train it for a few epochs, and then once it's done, we'll get the intermediate features. We'll basically pull out part of this neural network given new inputs. And pass those representations to a linear classifier on top of those features, and then compare against the baseline, which is just a classifier on top of the raw pixels. So here's our code. Again, we're going to use Torch for this. We're going to load the data from this set of functions. Torch Vision is important, so if you don't have it and you want to play around with it, you just have to install it, but it's all in pip. So here's where we load our data set in lines 13 to 15. We load the train data set, so train is true. We load the test data set, train is false. We're going to download them. The transformation here is just basically applying some normalization to the data. So the transform is transform, which we define over here. You can again take this as read. This is a bit beyond the scope of what we're talking about right now. We subsample just 5,000 of them and then load the data. So we haven't done any training yet. This is where we do the training. Again, this is ahead of ourselves, so I don't want to talk about it too much, but suffice it to say that, here I go again. Convolutional network is just a sequence of layers of neurons, so we use NN sequential from PyTorch. These have layers which are convolutional and two-dimensional, which is the subject of a future module. And those layers are followed by ReLU activations like we talked about in a previous module. So it's just a few layers of convolution of particular types of neural network layers and nonlinear transformations in ReLU. And then we have a max pool, which also we talked about in a recent module. And that's it. That's really all it is. Here's how we pass information through the neural network. We, again, have to send everything to this device. So we find the device that we can use. It's either something with CUDA on it, like NVIDIA or AMD, certain kinds of AMD chips, or it's a CPU. We push the neural network to the device. We set the criterion. This is a cross-entropy loss because it's a classification task. We choose the optimizer because it's Atom, and we're done. Here's where we actually do the training. So again, nothing new here. We, in this case, do we do batches? No. We, for every x and y, we send x and y to the device, and we zero out our gradients again. We get our logits from the model. We pass those logits in the criterion. We do backwards, so we compute all of our gradients, and then we optimize our parameters. And we do this a number of times. This is training for one epoch only. We're only going to train for 5 epochs here. So this is the loop where we do the training. Here's where we can investigate our losses and our training accuracy. So the loss keeps on going down. It's about halved after 5 epochs. The training accuracy doubles, essentially, through these 5 epochs. And we could keep on going. All of the regular caveats regarding training and stopping and regularization and everything would apply here, but just for the sake of argument, this is enough. In practice, also, like, again, you know this already, but I just want to reinforce it. I don't really care too much about the training accuracy because I'm always optimizing that, but what I want to see is how well a model optimized on the training set will perform on some other data, in this case a validation set. So I'd also be tracking that in reality. Again, I'm cutting corners for this little demo. Yeah, so again, also one thing I care about here is feature extraction. I'm not really necessarily only tuning performance, although anyway, like the point is getting a good feature extractor here, so I'm not going to necessarily put all the bells and whistles into this training process right now. Now is where I take the trained model, trained on CFR10. I'll chop off the classifier that I just added a moment ago, the thing that did the that applied the criterion, and I'll run the images through it to get d-dimensional feature vectors from the previously penultimate layer, and then I'll treat these vectors as representations, and then I'll train a new very simple linear classifier on those, like I threatened you a moment ago with. So here's where I extract the representations. Here's the model. And this is where I just extract the representations given the model and given all the other parameters, the loader and the device where I put the model. So I extract the representations for the training data, and I extract the representations for the data in the test set. So now I have my representations for training and my representations for testing in each of these cases. So the train loader basically encapsulates my training data, the test loader encapsulates my test data, and I pass those here. That's basically it. Yeah, so the result is I have 5,000 samples in my train set, and I have 256 dimensional vectors. So I've taken my representations down to 256 dimensions. I have my test data. I have 10,000 of them. Again, this isn't really a train test scenario like we've seen so many times in this course before, but I'm just getting representations through my training, my so-called training, and I'm going to use those for this task. Now I go back to sklearn, I get my logistic regression, and here's where I collect my flat pixels from the original data. So I get my representations of the training data and the test data in their original form on lines 16 and 17. So I get x train flat, y train flat, x test flat, y test flat. So I have my x's and y's training and testing in the original space. And I have, from the previous slide, the representations of the training and test data in my transformed space from Z, which I acquired from the convolutional neural network. I have my logistic regression. Here is a model trained on the original data in the original space, and I get my regular metrics on that. Here I train my linear classifier, my linear regression, using my transformed representations Z. So this is where I actually do the training on line 30. And then again, I can get my metrics from accuracy score. Again, it's useful to mention that everything else is the same in terms of my classifiers. There's multinomial, which is just saying that there's more than 2 classes. I train these for 200 iterations each. And then I just report the overall performance. And now I see like test accuracy in given the raw data X in terms of pixels, I get about 28% accuracy. And if I first take those pixels and pass them through my encoder, my CNN encoder producing these representations Z, I get up to about 54.6% accuracy. So a big jump in performance by first, representing them in this learned space Z. Here's just hammering this home again. Here's my test accuracies, but here's, not only have I drastically improved performance in terms of my task, but I've also done so with an order of magnitude fewer dimensions. So the flattened pixels, if I were to represent everything in the original space, is a bit over 3,000 dimensions. But if I push that information through a encoder, my CNN, I can do much better with far fewer parameters, which is kind of what we're always looking for. This is the great result I was talking about before, where like I don't have to do any trade-offs. Test accuracy improves drastically, and I do so in a far more efficient manner. Here is just a regular visualization of principal components analysis of our CNN representations. In some sense, this is even worse to my eyes than the PCA of the original space. It's a lot harder to draw straight lines through this representation, but I wanted to include it for completion's sake. So that's the results. Using our checklist, how well does CNN now? How good is the CNN representations of a representation according to our checklist? Are they expressive? So the CNN features live in this 256 dimensional space, and they're still able to capture complex patterns. So they're very expressive. They're very task aligned, obviously, because a simple linear classifier on top of these features outperform linear classification on the raw pixels. So they're very task aligned. Are they invariant or equivariant? I didn't actually do very many experiments there, but you can again take the original data, apply some noise, translate them, maybe rotate them a little bit, and see if the representations you get are still going to be useful for your classification task. And are they reusable? So can I take the same CNN encoder, give it data from another data set, like CFR 100, for example, and then train a linear classifier on that new task on this new data set and still get pretty good performance. I should mention I cut a lot of corners here. Like if I really wanted to, I could have been more aggressive with regularization. I ought to have also compared apples to apples and somehow either reduced the dimensionality in my original space X to be comparable to 256, or had larger representations out of the CNNs to make the the mere number of dimensions I had in my representations not so different. Maybe the benefit I get from doing CNN first is really just the compression and not the information that's in the individual variables of the compression. But again, this is left to you to explore and do experiments with. The key lesson here is good representations is one in which we can have very simple downstream models that will work very well without having to learn fancy new geometries for the task that I'm trying to learn. So in summary, evaluation has to remember for what we are optimizing. We want to align the objective that you're learning. So phi is a learned representation. Is it supervised cross-entropy for classification tasks? Is it contrastive loss for a classification task? Is it reconstructive loss for encoding tasks? Whatever the task is, you need to know that in order to learn phi well. The metric you use to evaluate the downstream task is going to be important. So are we optimizing for accuracy, F1, calibration error, or something else? And you ought to be able to do some kind of diagnostics. So linear probes, like the one we literally just ran in the previous example, might be one form of diagnostics. Clustering quality might be another. Embedding plots, these are kind of subjective ways of looking at the representations, but we've seen how they can still be useful. So yeah, for linear probes, you can freeze your encoder, your representation phi, train a linear classifier, see how well it does. K-nearest neighbors accuracy and representation space, similarly. Are points that are close, do they often share labels for classification? You can just visually check things, like if you do a PCA or a TISNI or a UMAP, are those representations now, like do they appear to be good according to criteria that we talked about previously in our PCA and TISNI modules? And again, the same caveats that we had before apply here and will always apply. Just because a graph looks pretty doesn't necessarily mean that you're learning anything from it or that the representation in the picture is useful for your task. So there's other practical proxies. So like sample efficiency, how much label data do you really need to reach a target accuracy with a simple head? So here we didn't do that experiment either, but we could have drastically subsampled the test set, the training set, and we could have done experiments to be like, can I get good performance on a 10 classification task if I only use 10 samples from every digit, or 20 or 30 or 40 to train the model. So this will tell us something about the efficiency of the samples that I need to use to have available for training, given an encoder that I already have that produces my representations. Again, if the idea is a representation already has the classification in mind, so I don't need to tell it very much in order to produce a good classifier. If you're doing unsupervised training, things like silhouette score, NMI, array, ARI versus ground truth clusters could be useful. So we don't really talk about clustering very much in this class, but you've probably seen silhouette score at least in a previous course. And again, how robust are they? This is an experiment that is really left to you to do, but take the original data from the previous worked examples and then apply some transformations or add some noise to them and see how well you do on the original space versus the representations, and see and think about what that might tell you in terms of how robust the representations are. Each of these are very task dependent. Again, this is one of our, how do I do this? Each of these are task dependent, so there's no like universal goodness score that works for everything, and that's by design. Like there's no like making things that simple. It would be ridiculous. Again, this is just for you to look into. I wanted to highlight some real world systems and some research threads that you can pull. I mean, you're all third year students, so you might be considering doing fourth year projects, including like little project courses with machine learning people at the university. So I want to mention just a few threads you might pull on in your fourth year. So there's image to text models. We're going to talk a little bit about this in the next module, but this basically is where you learn embeddings of both images and text captions together, and then you can use those like text and images represented in the same space to do zero-shot classification. Of course, large language models we're going to increasingly see in this course. This goes back to some of the early work with BERT in particular in 2019. But yeah, embedding tokens, which are basically representations of words or parts of words and their context. This is going to be the backbone for tons of tasks involving language. In fact, this paper helped usher in this new era of natural language processing. Graph embeddings we don't see very much, but there's a lot of interest in representing nodes in a graph as vectors, and then using these vectors to do the kinds of tasks that are relevant for graphs. So if a graph is a representation of a social media network, for example, or the links for pages on the web, or the relationship between songs in your library, or movies or shows in your library, or transactions being made and people making the transactions for the purposes of fraud detection. These are all tasks that often live in graphs. If you can represent these graphs as vectors and then use those vectors in a neural net model to do prediction, that's an area of a lot of interesting work. And the kind of questions you might ask is, well, is there better measures we can apply for representations than the ones we kind of waved our hands at? Are there measure representations that are maybe not so tied to the task, but are nevertheless relevant? Fairness and privacy is a whole sub-area of machine learning research. So can we have representations that ensure the fairness of those representations and the privacy of the individuals who formed those representations? Can we design objectives that are going to be more universally useful for embeddings? So again, a moment ago, we trained a CNN essentially to do classification just on the CFAR 10 task. But does that generalize well to other vision tasks? Who knows? But there's a lot of work in the area to try to produce objective functions that produce more universally useful tasks. So these are all some fairly straightforward areas you might get into, and there's dozens of others that I'd highly recommend you consider for research in the area of machine learning and artificial intelligence. Here are your quick checks, and here are the references. It's been a pleasure. See you next time.